everyone. This is a weekly TCS seminar at the Jagiellonian University. Today, our speaker is Giannos Stamoulis. Giannos works in Warsaw, University of Warsaw, PhD in 2023, Montpellier. Giannos is already known for his nice work on testing minors. So if you can test if H is a minor of an input graph G in almost linear time, and some further work is developing in this direction. Today we will see somewhat related or not stuff with the relevant vertex technique, probably not so relevant. It's great to have you here, Giannos. The floor is yours.
Thanks a lot for inviting. Yes, so this joint work with Petr Golevac, Stavros Koliopoulos, Dimitrios Tilikos. And in fact, it's a work that started more than 5 years ago. But only now we managed to write it in a nice and general way, these results. And in fact, the results that I present here will be announced in upcoming SODA. Okay, so the title is Finding Relevant Vertices in Linear Time on Bounded-Genus Graphs. So I guess to start explaining what happens here, I have to explain what is the irrelevant vertex technique. That in fact is a technique that in essence describes a simplification procedure. It's a win-win approach. If the instance of my problem is simple enough, then typically I can solve the problem easily. If the instance is not simple enough, then basically I have a mechanism. The relevant vertex technique gives me a mechanism how to simplify my graph and get an equivalent instance. And when I say simplify, I mean remove some vertices, find some vertices, remove them, and the removal of these vertices doesn't affect the fact of having a yes instance or not. So this technique was introduced by Robertson and Seymour in graph -13 to solve the k disjoint paths problem. What is this? I give you k pairs of terminals in a graph, and I ask you to connect them with a flow that respects the terminals. So it's a guided flow in a sense. And let me now show you how, basically give you an idea how this technique works for the disjoint paths problem in planar graphs. So to find relevant vertices, I need to look in nests. What is a nest? Is a collection of cycles embedded on a disk. The outer cycle is bounding a disk. The next cycle is inside this disk, and so on. And the terminals of my problem, for the disjoint path problem, are outside this outer disk. And I also have the interior of this nest, that is the inner disk here. And when I speak about the nest, I will demand these conditions. So this kind of planarity, terminals to be outside in the exterior of the nest, and the interior here to be non-empty. So what happens if I have such a nest? What I can do is I can imagine a solution for my problem, some collection of paths, and this infrastructure of this nest allows me to reroute the paths, avoid the interior, and in fact, the vertices that are in the interior have nothing to do with the existence of solutions. So I can easily throw them away. This is safe, so I simplify my graph, and I continue. So this is the win-win approach that I have here, where the notion of simplicity that I follow here, before I describe the relevant vertex technique as a simplification procedure. So what does it mean simply? Basically, it means to have small treewidth. If I have small treewidth, then in fact, I can solve the disjoint path problem in linear time using dynamic programming. And if the treewidth is large, then the idea is that large treewidth gives me a large nest. And once I have this large nest, this nest certifies that its interior is relevant. So I can just completely erase these vertices from my problem. And this doesn't affect the status of the instance. So this is the idea. Okay, yes. So this is the idea: small tree width, I solve the problem; large tree width, I remove relevant vertices. Here, I didn't give the definition of tree width, and in fact, you don't really need it to understand what's happening. What you need to know is that basically, if I have bounded tree width, I can solve a bunch of problems using dynamic programming, and this subtracted using this understanding. We have through Kurzweil's theorem that in fact says that if I have a problem that is expressible in counting monadic secondary logic, anyway, monadic secondary logic, so I can quantify on vertices and vertex sets of the graph. I can also have some counting predicates. Well, if my problem is expressible in this logic, then in linear FEV time, I can solve the problem when the tree width is bounded. So algorithmically, if I have bounded tree width, I can solve my problem, as long as this is expressible in CMSO. Also, I have the grid-minor theorem that says that large tree width gives me a big grid minor. And how do I use a big grid minor? Basically, grid minor gives me a nest, because I can just get the grid gives me many cycles. So here is my nest. Last thing, once you get the nest, how to prove that really the interior of the nest is relevant. And this, in fact, is the most tricky part. This is not easy at all to show. Basically, to show why irrelevant vertices are really irrelevant, can be safely removed. This requires a lot of work. And a result that you can get as a byproduct of the unique Lukens theorem, the main combinatorial base behind the relevant vertex technique, is the following result: that there exists a function that I will call the linkage function that says that if I have a large enough nest, then the interior of the nest is relevant for the disjoint path problem.
So is it all in the planar setup now, or it's in general?
We can think of the planar case here. Because in fact, when you go to more general graph classes, then really a nest is not. So keep in mind these three results: Kurzweil's theorem, grid-minor theorem, and this corollary, because we will use them. And why do we like the relevant vertex technique? Because in fact, it doesn't solve only the disjoint paths problem. It also solves minor containment. You want to check if the graph is another graph as a minor. It solves the rooted variant of this problem. I give you some roots, and now I ask for the existence of a minor that is rooted in these vertices. And graph modification problems, for example, remove some vertices so that the resulting graph is planar, or exclude some other graph as a minor. Topological minor containment, also the algorithm that we have to check if a graph contains another graph as a topological minor, also uses the irrelevant vertex technique. And this understanding recently, it is abstractized in some sense, in some recent work, in algorithm meta theorems. So we manage to, what we try to do is to identify logics that express, in a sense, the problems that are amenable to the relevant vertex technique. So all these kind of settings, all these kind of problems use the relevant vertex technique and many more. It's a technique that is very, very well established in the parameterized algorithm community. And typically, the algorithm scheme that this technique follows is the following. While the tree width is large enough, as long as the tree width is large enough, then find me relevant vertices. When the tree width becomes small, solve the problem using dynamic programming. And if your problem is expressed in MSO, then you just don't even need to write the dynamic programming. Kurzweil's theorem will give it for you. So what's the running time of an algorithm that works like this? Well, for rooted minors, and of course disjoint paths that are a special case of rooted minors, we have cubic time algorithm. The original algorithm was cubic time because to find an irrelevant vertex, you need to spend quadratic time. So quadratic time to find a relevant vertex, you repeat this loop linear number of times, so you get a cubic time. Well, finding an irrelevant vertex was improved, like this procedure of finding the infrastructure that gives you the irrelevant vertices was improved to linear time by Kobayashi and Reed. And in fact, this improves, this gives a quadratic algorithm for these problems. And recently we had almost linear time algorithm that basically allows to find each irrelevant vertex very fast. I don't want to get more details in what's happening here. I think a persistent question is whether we can get really linear time. And in fact, this is not something that's completely exotic, because for certain problems, we already have linear time algorithms. For example, planar disjoint connected subgraphs and generalization of planar disjoint paths has a linear time algorithm. Embedding a graph in a fixed surface, computing the crossing number, computing if you can remove some vertices to planarize your graph. All these are examples of problems that admit linear time algorithms. And in fact, the algorithms, these algorithms in these papers are heavily based in geometric topological properties of the problem. So the question is, okay, can we give a general framework on finding irrelevant vertices? How to apply this technique in a general way and have linear time algorithms? And if we want to answer this question, we have to ask ourselves, is it always true that once you give me a nest, always the vertices in the interior should be relevant? And in fact, this is not the case even for minor containment. So in minor containment, if I have a very large nest, this is not enough to certify that the interior of this nest is relevant with respect to the minor containment problem. Why? For example, you look at this graph. Here I give you a model of two grids connected to a vertex. And now what you would like to do is to reroute this graph to try to draw it like away from the interior of this nest. And here you can, if you try a bit, you can see that the graph, the grid that is inside here, cannot be easily drawn. Cannot be drawn, in fact, using only the nest. So in principle, if you have only cycles around this part of the graph, in principle, you cannot use the cycles to redraw whatever is inside here, to redraw it a bit outside. So what happens here is that if you also ask for the existence of many rails in the nest, many paths that cross the cycles, then here you have all necessary infrastructure to really draw your graph inside here. So for minor containment, we don't really need only a nest, but we also need rails. And once I have enough rails, then I can use these rails to reroute my minor models and in fact prove that the interior of the railed nest is really relevant for my problem. Let me give you this definition of what I mean by railed nest. In fact, I will speak about rooted graphs. I give you the graph, it has also some roots, and I will focus on surface embedded graphs. I already assume that you give me the graph with some embedding on some surface. And a nest is this, is a collection of, is a nest together with some rails that traverse these cycles in a monotone way. You're not allowed to wiggle forth and back. All the roots should be outside, in the exterior, and the interior should be non-rooted. Now, using the definition of rail in a nest, I would like to propose a general way, a property that says, that tries to abstractize this idea of finding relevant vertices. And this will be the insulation property. This will be a property of problems, of rooted graph problems. And to state this property, I need to give a definition of a pi irrelevant vertex. So a non-root vertex of a graph is pi relevant for this given problem pi if the removal of this vertex doesn't change the status of the instance with respect to this problem. And the insulation property is the following. A problem has the insulation property if there is some constant such that if you give me a surface embedded graph and if you give me a railed nest of this graph where the roots are outside this nest, then the interior should be irrelevant. So this is so this is the property that that I asked from a problem, and we already saw that disjoint paths and minor containment are two problems that have the insulation property.
Both the number of cycles in the nest and the number of rails is C.
Yes.
C pi.
Yes.
Okay.
So the main result that I would like to present is the following: that you give me a problem that has the insulation property.
It's very sorry. In the definition of a rail, you always insist that you go forward. Can you go backwards, forward? Is it allowed?
No. In fact, the intersection of every rail and cycle is connected.
Select this solution.
Yes.
Okay.
Here. So here, be careful, the constant depends on the problem. Nothing more. So this is the main result. That is a mechanism that finds in linear time, in graphs that have bounded Euler genus, finds a set I whose removal leaves a bounded-treewidth graph, and this set is relevant. So in linear time, I can remove a bunch of vertices without changing the status of the instance, and the obtained graph has bounded treewidth. Treewidth here depends on G, on a polynomial of G.
So it's like all steps together in linear time, yeah? Like
yes, in linear time, you pass the graph, you do some traverse of the graph, and in linear time, you get, let's say, all irrelevant vertices. Not all, but enough irrelevant vertices to certify that after the removal, you have a graph of bounded treewidth.
Right, so if you compare it to what was known in, say, planar case, for some particular problems, then there was linear time. No, there was.
For some particular problems, yes.
Yes. Okay.
Yes. For disjoint paths.
Okay, and now you found like an abstraction, and then a general.
Yes.
Mm-hmm.
And in fact, the algorithm corollary that we have from this is that if you give me a rooted graph problem, if it has the insulation property and is expressible in CMSO, then you can solve it in linear time on bounded Euler genus graphs. So the insulation property will give you this simplification to small treewidth, and the fact that this CMSO is expressible, you use Kurzweil's theorem, and then you just solve the problem. Okay, so this is these are the results, and yes, already the disjoint path problem have this property. The induced variant, when you ask the paths to be induced, and rooted minor containment and the induced variant also has this property. Hiding minors, deleting some vertices to exclude some graphs, some graph of the minor. All these problems have this this property. So for all these problems, we get linear time algorithms for bounded genus graphs. The question is, what about the other problems, topological minors, or these logical frameworks? Well, in fact, for topological minors, having even a railed nest is not enough. Because, for example, you can have a high degree vertex really deep inside the railed nest, and then you cannot really find this vertex somewhere else before, so you cannot redraw your graph. So this is some limit of the result. Okay, so in the rest of the talk, I would like to just comment on the proof of this theorem, how to find only relevant vertices in linear time. And here the main bottleneck somehow that we encountered before is that once you find the related nest, you process the graph, you find the related nest, this says that you should remove all the vertices that are in the interior of this related nest. Yes, but then maybe there is another related nest somewhere else. So you need to spend, again, linear time to find each one of these nests. So in some sense, you process the same graph again and again. So can we remove irrelevant vertices in big patches? So in an equivalent way, can we thin the graph in linear time? The approach that we propose is to decompose the graph into slices that are subgraphs of bounded-treewidth. In each slice, locally detect related nests, and then using this local computation, finally remove the irrelevant vertices globally and return this set of irrelevant vertices. Okay, to explain this, how do we do it? The first tool that we use is, we call it radial distance decomposition. Is a concept that somehow seems natural, but also we didn't find it in this way around in the literature. But anyway, let me explain what it is. You give me a graph Z. Now we speak about sphere-embedded graphs that are also two-edge connected. This is an extra assumption that I do that's a bit technical, but in the end, I can lift this assumption. And also I give you a root. So I speak about sphere-embedded, single-rooted graphs. What is the radial distance decomposition? I start from a root U, and then I work in the radial graph, and I take all faces, like I do a BFS in the radial graph. So I take all faces that are incident to the root. In the left, I will show you how to draw the graph, and on the right, I will construct a tree that shows the structure. So here, T0 will be the root of this tree that corresponds to the root U. Okay, so I take all faces, I put them in a single bag. Then I continue my BFS layering of the radial graph. So I take all vertices that are incident to the face that I had before. Here, I put them in a different, I group them in different bags. So I group my BFS layering in different bags. In which way? In a way that vertices are in the same bag if they are connected, they will be connected in the future, in the unprocessed part of the graph. So for example, these two vertices here, they will be connected. What they have in common is that they have a face in common that's not already processed. This face and this face. There is a possibility of the internal path in the future. Yes, yes. These squared vertices and this like vertices, they will not be connected in the future, so they are in separate bags. So I continue. I group the vertices in this way. So I continue. I take the next layer of faces. Everything is around. Then I continue. I take the next layer of vertices, and so on, and so on, and so on. And this way, I get my radial distance decomposition. Easy and natural. Okay, what happens here is that what I have, basically using the edge connectivity, the fact that in each edge I have two different faces and two different sides, I get that every vertex face edge of the tree. So here I have layers of the tree that correspond to vertices of the graph and layers of the tree that correspond to faces of the graph. I get for each such edge going from vertices to faces, all these bold edges, I get a cycle. You can see it also. This is something that I can prove. The proof is a bit technical, but somehow easy. And here you can see that every time that you have, let's say, you have this edge that is basically corresponding to this bag of vertices and this gray face here, you have this cycle bounding the future. So for every vertex face edge, I have a cycle. I call it root aligned cycle of G. So when I speak about root aligned cycles of G, I will speak about cycles that are obtained through this process. And if you give me a long path in the tree, then this corresponds to a sequence of nested cycles. And a property that you get from the construction is that the root aligned cycles of G are non-crossing. The way that you take your layering will give you cycles that are laminar. Okay.
So this they don't have to be vertex disjoint, right?
No. For example, the cycle here you can see two cycles like this, the one that corresponds to this edge and this edge, that are this one and this one.
So I kind of understood before that the nest collection for disjoint cycles, but it's not.
It is.
It is.
But if you give me, for example, what is a path here? It starts from T0, it goes here, 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 here. Okay. So the cycle that you get is this cycle,
yes,
is this cycle, and this cycle. The cycle bounding this pink area, the cycle bounding this yellow area, and the cycle bounding the green.
Okay.
So as you go through the nest, they are disjoint. But in this construction, different nests can branch in some sense. Yes. This branch don't have to be disjoint. Okay, so once I have this radial distance decomposition, well, of course I can compute it in linear time. It's just a BFS, and I will use it to define what we call a slice. It's a chunk of the graph that basically is built from a cycle, a root aligned cycle of the graph. So we just pick an edge from vertices to faces in this decomposition. This is a cycle in the graph. And then you proceed inside the tree for, you give me some Z, you proceed for 2Z layers. And here I ask this to be even, but I think it's not even even. So in another way, if you see this part, this is what's happening. So you start from this edge and you proceed for 2Z steps. So you stop in these edges that are also vertex face edges. This also corresponds to cycles. So this is the picture that happens in the graph. You have a cycle, and then you go in Z, in radial distance Z, and you get to this collection of cycles. So a slice is the graph that is basically the graph that is embedded in this closed disk bounded by this blue cycle. You crop and you take this graph, but also you throw away whatever is in the interior of the cycles. So you take this kind of pseudo disk. So this is a slice. Take a cycle, you go some steps, you flood the graph in a way, you stop after some point, and you just forget what's after. Important observation, the tree width of this graph is bounded by the depth of your construction. And so this is a bounded tree width graph. And in fact, an extra property that we have from the construction is that if you pick a red cycle here, then between the blue cycle and each such red cycle, you have a big nest. Why? Because you spent Z layers to go, and this was the property that I had before, that in a long path inside the tree of my decomposition, I have a really large nest. So this is what's happening. Like I have the cycle on which I did my slice, and I have the inner cycle here, and I find the nest corresponding to this cycle. And the question is, okay, for each cycle, I can find a nest. But can I also find a railed nest for each cycle? If I had a railed nest, a big enough railed nest for each cycle, then let me not show you this. If I had a very large railed nest, then this would mean that I have the infrastructure to apply the insulation property. If I had many paths going from here to here, big flow, then this flow, together with these cycles, gives me a railed nest. The insulation property tells me that everything that is here is relevant. So I can just get rid of all the vertices that are here inside in the future of this decomposition.
Just one of those cycles.
I can do it for one. If I imagine what happens if I take a flow, if I say, okay, here I have a flow, I remove insulation property tells me that I can remove whatever is inside here. But then if I go apply for this cycle, then maybe the flow that I had before maybe enters this part. So this is what's happening. I cannot guarantee that the flow that some flow will enter these parts of the graph. So what I would like to do is to compute, to detect all rail nests of G that are captured by this slice. And the problem is that now I see a local part of my graph, and I'm not sure if in this part of the graph, the local information that I have about flows, if this is really corresponds to the global picture. So to circumvent this problem, I look in slightly bigger slices. So instead of taking, I imagine my slice split into two levels. So this is the gray is the first level of my slice, and the yellow ones are the next level. So in fact, I look from this blue cycle down to these small cycles. This is my slice. But I also pinpoint some intermediate cycles here. Now, the idea is that still, I want to find a flow from this cycle to this red cycle. And now I want to say that this flow, if such a flow exists in the general graph, then such a flow should exist in the slice. Meaning, if I remove the interior, all these green parts, if I remove all these interiors, then still I have a flow. So what do I have to do? I have to ask this distance.
You're looking at the flow between the blue
And this red.
And the red circle, and you say that if it exists in the general gray picture.
If it exists in a graph where I include the interiors, the green parts.
And green parts are in the future.
Yes, they're in the future.
Then they exist.
Then they exist in the part when I crop this part of the tree. So I just remove the interior of this.
Okay.
This, if it happened, I would be very happy because in fact I can just focus on the flows only in this part of the graph. Yes. That also has bounded treewidth. So this is indeed true because I can ask the distance from the red intermediate cycle down to these smaller cycles, further in the decomposition. I can ask this distance to be as large as the Lincoln function. So in fact, if I have a flow with the terminals being in this gray area, then this flow by this theorem should not go deeply inside the green part. So if I have a flow that enters these green worlds, I can apply this lemma many times, and I can reroute my flow to avoid these parts. So I really need to have this buffer given by the Lincoln's function in order to avoid my flow entering this. If this happened, once this happened, now I'm very happy because in fact, I can pinpoint all intermediate cycles, all red cycles that have a k flow to the other cycle by just looking in this slice. I don't have to look what happens in the future. By just restricting myself to this slice, I can check if I have a flow or not. How can I do it algorithmically? My graph has bounded treewidth. I can write the existence of this flow in MSO. Purcell will tell me for which cycles this flow exists. This is the key idea. Once I found the cycles, the intermediate cycles that have a big flow to the other cycle, then let's say that these are the bold ones here. For these ones, I have a flow. For the others, I don't have. If for these ones I have, the insulation property tells me that I can safely remove the interior of these inner cycles. So this is what happens. I take a slice. I just look for these intermediate cycles for which of them I have a large flow. Cell state.
But for each, there is a flow. It's not a flow to all of them.
Yes, for each one.
For each, there is a flow. Okay, so you have these three. Then what? Then you can, each flow you can reroute.
Then if I have a flow, then for this cycle, if I have a flow, this means that I have a railed nest that whose inner cycle is this one. So this means that I can remove the yellow and this part, everything. I choose not to remove the yellow. I choose to remove only this part because this is the one that I'm sure that if I remove, I will not destroy the flow of the others. Yes. So this is what's happening here. For every cycle that sends a big flow to the blue one, I remove not the whole interior, I just remove some part of it. But still, this is enough. And this is how the proof of this theorem goes. Like, I have this algorithm that I call thin that proceeds in the following steps. I decompose my graph into slices of appropriate size. How do I do it? I compute the radial distance decomposition, and then I just chop the graph into parts. I process these slices in some order. For each slice, I find all the intermediate cycles sending a flow to the outer cycle. I empty the interiors, the inner cycles, and this is how the whole procedure goes. So I start with my first slice. I just chop some subtrees of this decomposition. In the one that remain, I just proceed and chop and chop and chop subtrees. And I output this set of vertices. Why these vertices are irrelevant? Well, the insulation property tells me this. A bit more tricky, why the tree width after this procedure is bounded? Well, the point here is that imagine that I apply this procedure. I remove all these vertices. Imagine that still I have a very large railed nest. This railed nest should appear somewhere in the graph. And in fact, I can prove that it should appear in some slice. Maybe not this nest itself, but if I have a large nest in the whole graph, then I also have a large nest, a railed nest, in the slice. So this means that I should have a large flow. Contradiction, because whenever I had a large flow, I processed my graph. And that's it. This is how I prove this lemma. And let me mention here that this proof, it sounds natural, but is a bit it sounds a bit intuitively understandable. However, it's a bit technical to really prove this. Okay, so this is how I found a bunch of irrelevant vertices in linear time by processing these slices one by one. I spent linear time in total, but this is for planar graphs. Here I write rooted, but basically I mean single rooted. But I promised in the beginning that I speak about rooted graphs, multiply rooted graphs, and also embedded in big surfaces. So to lift to this case, I need the following lemma. I just need a reduction to the planar case. The reduction is guided by this lemma that says that if I give you a rooted graph G that's embedded in some surface of a of Taylor genus C, then in linear time, I can find a set of edges that I can contract to obtain a planar graph. When I do this contraction, I also include all the possible roots that my graph had. And after I do this contraction, the graph is planar, and also the tree width of the new graph, of the contracted graph, is not that different from the initial graph. Believable. Why? Because we know how to find, how to contract parts of the graph to kill all handles. This is a result that we get from a paper of Cabello, Vatier, and Neverus. And basically, we work the radial graph, we find shortest paths in the radial graph, and we use a result that says that you can find such shortest paths whose contraction kills all handles of the surface. And well, for the tree-width bound, we use another result that says that if you have shortest radial paths, and if you have a large railed nest, then these paths, the shortest radial paths, should not go deeply inside this nest. This is a result from Demain, Hazagai, and Kawarabayasi. And we use this to show that if I have a very large wall in the surface embedded graph, then after I do the contraction, a big part of this wall should survive in the planar graph. So if you bound the tree width of the planar graph, this should also bound the tree width of the surface embedded graph. And in fact, here I speak about shortest radial paths. Here I speak about edge sets. So there's a bit of a technical hiccups how to get from these shortest radial paths to really what edges you need to contract in order to get this planar graph. In fact, they are all the edges that are incident to faces that are captured by these radial shortest paths. All the edges here that are adjacent that are incident, to colored faces. Anyway, and this is what I wanted to say about how to lift to bounded genus graphs. And well, to conclude, just let me mention some open problems. Well, I said that what we have now is that if you have the insulation property and your MSO expression, it's the case for all these problems, and then your problem can be solved in linear time on bounded genus graphs. So what about going beyond the insulation property? So we already saw that topological minor containment is an example of a problem that doesn't have the insulation property. This is a kind of counterexample. But in this kind of this problem belongs to a general family of problems that have some weaker insulation property. In fact, when you have a railed nest, you cannot say that every vertex in the interior is irrelevant, but there is some vertex that is irrelevant. And of course, to find this vertex requires extra job algorithms. So the next challenge is to try to apply this framework, to apply these decompositions, and not work with the insulation property, but with this kind of weaker insulation property.
Do you have some natural example of a problem that satisfies this?
Topological minor containment.
Why is it so?
Because of this example, shows that the insulation property that we have is not enough.
Yes, but then why the new one is okay?
Because in fact, well, here, the idea is that if you have a very, very large nest, it's not that every vertex is relevant. There should be some irrelevant vertices. In fact, here, all these low degree vertices are not essential for the inside here. But if you make this super large, then at some point you can remove Imagine that here you have a very large nest. Also, you could remove some vertices still. So there is a simplification procedure also for topological minors. You can find relevant vertices, but the problem is that you don't know exactly where to find them. There is some extra work to be done. And all these algorithms that use irrelevant vertex technique, but in these more general settings, in topological minor containment, also in the logical frameworks that I mentioned, they ask for this kind of weak insulation property. So this is the next challenge. Also, another question, comparing also to previous algorithms. Okay, we achieve linear time, but it's a bit unsatisfying that we go up to bounded genus graphs. So the question is, H minor free graphs or general graphs? Can you apply this approach really to this, let's say, H minor free graphs? It's not so direct because here the approach is heavily based on taking this radial distance decomposition. So in fact, you have to take the radial graph. But maybe there is some hope using ongoing research, linear time algorithms. Maybe in the future we can see some. That's it. Thanks.
Thank you.